degree by 4 pi r square. Okay, this we have to take. We have taken BS law. BS law is this, you know, mu naught by 4 pi ideal sine theta by r square. You remember this. Okay. Now we have to take dB equals mu naught ideal sine 90 degree. So this is what, this is going to be 1. So finally dB equals mu naught by 4 pi r square into IDL, or simply we can say mu naught I into mu naught I upon 4 pi r square into dl, right? So this we have to take into account. This we got. This is due to this current element. You can see this. Okay. Now what? Now we will do magnetic field due to the entire circular current. So what do you think here is to be integrated? This dl is to be integrated. This is the element, right? Element of the circular current. dl is to be integrated. When you will integrate this, what you will get? The entire length would be 2 pi r. So now dB would be, this B would be what? Let us take this. We have got dB equals mu naught I upon 4 pi r square into dl, right? Now what we are interested in finding out? The entire circular current, right? For the entire circular current. So what would be the circumference? The circumference would be 2 pi r, right? So the constant would be taken out of the integral symbol, 4 pi r square, because you know that if we know the magnetic field, if we know the magnetic field due to this current element, and we are interested in finding out the magnetic field due to the entire circular current, what we will do? We will integrate, right? So we will integrate this dl element, because this is the only element, only thing that is to be integrated, otherwise all stuff are constant. I have taken it out of the integral sign. Now what are the limits? Limits are from 0 to 2 pi r, right? Now what will be this? This is very simple. Mu naught I upon 4 pi r square into 2 pi r, right? If you will integrate this, you will have 2 pi r. So what is the final result? It is mu naught I by 2 r, right? Now one thing that we need to understand is that if current is anti-clockwise, we are aware of this fact that if current is anti-clockwise, then what is going to be the direction of magnetic field? It is going to be outward, right? Outward. Or if you consider this board, you consider that, okay, this board is along xy plane, this is x, this is y, so z-axis will be perpendicular to this, so we may put it in vector form as this, right? So one thing that we have to understand, that in order to express the direction of magnetic field, we have two options. Either we can put it in vector form like this, you are able to see here, or the other way is you can put it in this manner. This is the magnitude, and this you will put. This will show that magnetic field due to circular current, right? Circular current in the direction anti-clockwise. Current is flowing in anti-clockwise direction, then the magnetic field will be directed outward, normal to the page. This is we had talked about this in the last session, right? Magnetic field is out of the page, right? This is another way to express the direction of magnetic field. Okay, you got the point? All right. Now let us take one question based on this. Okay, you have one circle, you have another circle. In this, current is flowing I. In this also current is flowing I. But One thing is, this one is clockwise. The direction of current in this circular conductor is clockwise, and in this it is anti-clockwise. The radius of the two will be is R1, okay, and this is R2. That we need to understand. So what we do, what we need to find out the magnetic field. Obviously net magnetic field at center of the two coaxial circular current, of two coaxial circular current. How to get it? Circular current, you know, it is very simple. Okay, we need to take into account the direction of magnetic field, right, as well as the magnitude. So let us solve this. First of all, we need to talk about the magnetic field due to the first one, this one, right? So it is mu naught I by 2 R1, and the magnetic field is along z-axis. If you consider this to be, this plane is along, that means this circular conductor is placed on the xy plane. In that case, the magnetic field will be directed along positive z-axis if current is anti-clockwise. It will be negative z-axis if current is clockwise, right? Okay, so this one anti-clockwise current, what you will get, this is positive K. All right, now this is for the second conductor. Second conductor, it would be mu naught I by 2 R2, and the magnetic field is directed along negative z-axis. And why it would be negative z-axis? Because this current is clockwise. When current is clockwise, magnetic field is into the page. When you are saying into the page, that means it is, you know, if this is along x and y, I have told you x and y, outward is positive z-axis, inward is negative z-axis. So that way we got this. Okay, ask yourself, I think it is clear now that magnetic field is a vector. So what we need to do, if we have to find out net magnetic field, how we are going to do? We are going to add them vectorially, right? Vector sum of the two magnetic field, right? Vector sum of the two magnetic fields. So B would be B1 plus B2. Okay, so what is going to be? Just have a look. B equals mu naught I by 2R1. Yes, this is positive. Okay, and then we have minus of mu naught I by 2R2, and this is positive K, right? So what is the final answer? Mu naught I by 2 could be taken out of this. This is 1 by R1 minus 1 by R2, and this is along z-axis. So this is our final result, right? So this is very, very simple. We need to understand what is the direction of, if you have got multiple conductors carrying current, then you need to understand what are the directions of magnetic field due to individual conductor. So we found the magnetic field as well as direction, and then we added them vectorially, and then we got the final result. Okay, now let's move on. The next topic, our next topic would be, okay, here I'm again putting it, the final result. The final result B would be mu naught I by 2 R. If it is anti-clockwise direction, current is flowing in this direction, then what? It is going to be outward. So this is outward. Okay. So this is our result. Magnetic field due to circular current at the center is this. This is very, very simple. Right? Now, let us move on. find out the, okay, one thing that we need to understand. This is the direction of magnetic field. If you have placed this circular current like this, you understand this very simple thing. If you have got the direction along the curl of your fingers, magnetic field at the center, just have a look. At the center it is straight, right? As you move from the center towards the end of this, what do you see? That these lines, magnetic field lines, are getting curved, right? Okay, so, and here you see that these are the magnetic fields, loop of magnetic field lines, right? Okay, so this is the direction of magnetic field. We need to be very careful about this, that magnetic field due to circular current, how, because this is important question actually. They can ask you, show the direction of magnetic field due to a circular current. So this entire, diagram is required in that case, right? They may ask you for 1 mark in boards, right? In boards they may ask you for 1 mark. Okay, so this we need to do. I want you to practice properly, and see, don't retain any diagram, don't memorize like, okay, this is the diagram, I will draw it. No, there is logic, there is some logic behind it. Try to understand the logic. Try to understand the logic also. Okay, all right, now let us move. Why this is in this particular pattern, right? That is important. In any diagram, throughout the physics, throughout the syllabus, in physics, whatever you do, any diagram, you try to understand why that pattern is there. क्यों नहीं किसी और तरीके से बनाया गया? क्यों ऐसा है कि ऐसा ही ये पैटर्न है? यही पैटर्न क्यों होगा? राइट? अगर हम ये ऐसी आदत डालेंगे तो हमें कभी भी ऐसा नहीं होगा कि अरे अभी मैं डायग्राम भूल गया. नहीं, डायग्राम भूल गया फिर बात ही नहीं आएगी. Because you are connecting the things logically. If it is like this, why it is like this? Why it is going to be, when it is closer, there are, concentric circles, closer concentric circles. You are saying, because here we need to understand something. Here, at the center, why it is straight, why these are curved, right? We need to ask ourselves and then move on, right? Okay. Quickly we will do this magnetic field due to circular arc, right? Arc of a current at the center. So here this is very simple. The way we did magnetic field due to circular current, there we had to take this dl to be what? 2 pi r, r into angle for circular, for complete circle. Here it is not complete circle, here it is an arc. Arc is what? Length of arc will be radius into angle. We are aware of that. So that one simple thing we need to put here. Okay, so let me recall this thing. B, help you recall, right? dB equals what? Mu naught. Okay, here also one thing, here also we need to understand ideal is making 90 degree with R, right? 90 degree with R. So what you will get? Mu naught I by 4 pi R square into dl, right? This is the thing we are getting. Okay, now B would be what? Take this constant out of this, integral sign, r square, this is dl, and what would be the limit? Limit would be 0 to r alpha. What will be the final result? B equals mu naught I by 4 pi r into alpha. Alpha is measured in radian. Alpha, angle made by the arc, right? Made by the arc, measured in radians, measured in radians, right? Okay, so this is our final result, and one thing, again we need to understand, this is anti-clockwise current, so magnetic field here would be outward. So we may put it in this manner or we may put it in this manner. I had told you this, right? I have told you this, 4 pi r into, this unit vector along positive z-axis. Okay, so this is the end of the session for today. In the next session, we will do many questions based on this. Okay, be it NEET, be it boards, this BS law is very important. So we will do with our full energy, full understanding, full confidence, right? So in the next session, we will continue from here, right?